Hi, and welcome to our demonstration of our audio-to-MIDI converter, an application of the FFT to audio signal processing. As a group of mostly musicians, we are intrigued by the possibility of computer-aided music transcription, and how much easier that would make the process of learning new songs. Our final product is capable of taking audio data in the form of CSV files and outputting a MIDI file, which can be easily viewed by many music notation softwares. We will run our program on a sample from an Adele song, Rolling in the Deep. Here's what the original audio file sounds like. Now let's see how close we can get. While the program is running, we will explain our algorithm.
Music is waves, and to analyze waves, we use a Fourier transform, which converts data in the time domain to data in the frequency domain. The standard Fourier transform is O of n squared, which is too slow because there's a lot of data. The simplest fast Fourier transform algorithm is the 2-radix Cooley-Tukey algorithm, which works on discrete datasets through a divide-and-conquer strategy. The algorithm is O of n log n, but works only on datasets whose size is a power of 2. To generalize, we implemented the Bluestein FFT algorithm, which uses convolution to reduce any dataset to the power of 2 case.
Our program uses Fourier transforms in many different applications, the most fundamental of which is detecting the pitch of a given note. To do this, we take short, overlapping 0.1 second slices of the audio file and apply the FFT to each slice. This is necessary to isolate individual notes because the Fourier transform is difficult to analyze when there are multiple notes in a sample. Unfortunately, the resolution of a Fourier transform is inversely related to the size of the window, and our windows are too small to consistently give the fundamental frequency of a slice from a Fourier transform alone. We need to take advantage of more information, and there's more to be used. When a note is played, it has overtones that are multiples of the frequency of that note. Thus, instead of looking for the note in the Fourier transform, we should look for the periodicity of the Fourier transform. Thus, the Kepstrom algorithm takes the Fourier transform of the log of the Fourier transform of the slice and then returns the highest peak in the appropriate range. This gives us a fairly accurate view of the pitch with respect to time, as shown. This was our beta functionality, and this alone gives a not too terrible approximation of the Adele song, which we'll play now.
Luckily, we can do much better. To do so, we need to know when notes start. This is where our onset detection algorithm enters the equation. We use the method of spectral flux, which is described by these formulas. The first formula calculates the sum of the positive increases in frequencies from the FFT of one slice to the next. We take only positive increases in the magnitude of the Fourier transform because we want to detect onsets and not offsets. This produces a graph of spectral flux with respect to time, where the highest peaks are onsets. We apply a low-pass filter to reduce noise and make the peak-finding process easier. Finally, we have a peak-picking algorithm, which chooses points that are larger than all points within a small window. The peaks must also be larger, by delta, than the average value of the points nearby, with more weight given to the points before it. Applying the peak-picking algorithm to our low-pass spectral flux will give us the onsets of notes. These graphs are the result of running the onset detection on Adele. The first graph is a picture of the spectral flux over time. The second is after the low-pass filter has been applied, and the third graph shows the points that were chosen as onsets by the peak detection algorithm. We now have algorithms to find onsets and the pitch at that onset, so we should have enough information for our output. Let's listen.
You know what that sounds like? Wait, one more time? And that's our program.